So in the final video, I want to look at just a quick overview once again of each case. This is going to be a condensed discussion for each case of our linear systems, our homogeneous linear systems with constant coefficients. All right, so case 1, distinct non-zero eigenvalues. All right, we can write the general solution out. All right, in terms of e to the lambda t times its corresponding eigenvector and linear combinations of that. The long-run behavior is completely determined by the eigenvalues, lambda 1 and lambda 2. All right, we either get a sink, source, or saddle. And the thing that I'm going to highlight in each case is what the component functions look like. In this case, they're linear combinations of e to the lambda 1t and e to the lambda 2t. All right, we're also going to foreshadow what we're going to see coming in the next chapter at the end of this. If we have complex eigenvalues, we only need to use the complex eigenvalue with the positive imaginary parts, a plus bi. Using Euler's formula, we can still use the eigenvalue and eigenvector approach. V is still an eigenvector. It's going to have complex numbers in it, though, associated to the complex eigenvalue a plus bi. Expanding that out and just considering the real part and the imaginary part gives us two independent solutions, which helps us build the general solution. And once again here, the component functions of any solution to a system with complex eigenvalues are going to be linear combinations of e to the at cosine and e to the at sine. So if you get complex, you're always going to have that. Multiples, exponentials times cosines and sines. If a is 0, you're talking about a purely imaginary eigenvalue. All right, then you're going to have a center, in which case e to the at will be 1, so you'll just get sines and cosines. Otherwise, you're going to have the product, which will either lead to a spiral source if a is positive or a spiral sink if a is negative. But again, the components of a solution are going to be involving only e to the at cosine, e to the at sine, b, t, or just cosines and sines if a is 0. Okay, so that was case 3, or case 2. Case 3 was where we had one 0 and one non-zero. All right, this is a kind of an oddball case in the sense that you end up with other equilibrium solutions other than the origin. In fact, you can get a whole line of equilibrium solutions in this case. And the long-run behavior is determined by the sign of lambda 2 only. And the component functions, as highlighted in blue here, are linear combinations of e to the lambda t and also constants. You might get some constant terms in there. All right. Last case, repeated eigenvalue. In this case, we can't use the usual eigenvalue and eigenvector approach. We still need to find the eigenvalues. You need to know that still because that's part of the formula for the solution. The solution to an initial value problem is expressed in terms of its initial condition vector because v sub 0 is the initial condition vector. v1 is determined from that in the coefficient matrix and the eigenvalue lambda. And then you just explicitly write out the formula. It's e to the lambda t times v sub 0 plus t times e to the lambda t times v1. And the end behavior is determined by the sign of lambda, whether it's positive or negative, but, and it's highlighted in blue here, the component functions are going to be either involving e to the lambda t and t times e to the lambda t, assuming that vector v1 does not come out to be the 0 vector. All right, and that's what will happen more often than not. Or if it does happen that vector v1 comes out to be the 0 vector, then you're only going to see lambda t's, e to the lambda t's, pardon me, in there. All right, but that's going to be have consequences for us going forward when we talk about second order differential equations, which we've done a little bit already, and I want to just speak about that for a minute to end this video with. We've talked about second order linear differential equations before. All right, we've solved these differential equations by plugging in e to the st and solving for s, and we're going to do more of that going forward. But we've also seen how to convert this from a second order equation to a first order system by letting v equal y prime. That gives us the first equation in the corresponding system obtained by reduction of order. And then if we differentiate v, that's like taking two derivatives of y and plugging that into the differential equation, into the second order differential equation, we would get v double prime, or y double prime. I'm just going to rewrite it. We would be replacing here y double prime by v prime. Y prime is what v was defined to be equal to, so we get p times v plus qy equals 0. And then just rearranging that and solving it for v prime gives us the second equation in the system, which is that v prime is equal negative p, I'm going to write the y term first, negative q times y minus p times v. Alright, so let's just write that system in matrix form to finalize this. So again, we have this system, y prime equals v, v prime equals negative q times y minus p times v. Now, converting this over to matrix form, alright, to linear system matrix form, keep in mind here that the ordered pairs we're looking to solve for the system is not x and y, but it's y and v. So y is the first unknown. So the right-hand side of the first equation is actually going to be 0y plus 1v. All right, and that tells us our matrix of coefficients. When I write out the system in matrix form, we'll take the following shape. So capital Y is our unknown vector valued function, and it's going to be 0, 1 in the first row, and then negative q and negative p in the second row, times our vector capital Y, which is little y, little v. All right, now where this is going to pay dividends from our previous work on linear systems is we know how to solve this linear system. And we know what the general solution is going to involve. It's going to involve one of a few possibilities. Either we're in case 1, and we're going to have e to the lambda 1t and e to the lambda 2t is what our components are going to involve. Or we're in case 2, where we're going to have e to the at cosine of bt and e to the at sine of bt. We have a complex eigenvalue. Okay. Or we might end up, if we're in the third case, we might end up just with our eigenvalue lambda 2 and constants. Okay, or we might end up in the last case, which is still going to involve the repeated eigenvalue. Right, or in the repeated case, we only had one eigenvalue, which was lambda t, or which is lambda, pardon me, so we get e to the lambda t, and our components might also involve t times e to the lambda t. So what we're going to see going forward is knowing all of those things is going to help us to determine the solution of the corresponding second order equation. All right, because once again, we had the first order or the second order equation. From the second order equation and the reduction of order technique that we just went through, we end up getting the corresponding linear system with this coefficient matrix. All right, so there's a correspondence between second order equations and linear systems, and we can go backwards from that as needed as well too.